Okay, so this is 3.4, and this is the last section in Chapter 3 that we cover. We don't cover 3.5. In this section, what we're going to try and do is establish some kind of connection between the geometry that we've been looking at in Chapter 3, so vectors, lines, planes, things like that, and solutions to systems of linear equations. Trying to bring the algebra from chapter 1 and 2 into the geometry of chapter 3 somehow. So to begin with, we're going to look at equations of lines and planes again, but from a different perspective this time. So in the previous section, we came up with the point normal equation for a line and the point normal equation for a plane, derived in very similar ways. This time we're going to take a look at it from a different perspective and come up with what we are going to call the vector equations for a line or a plane. And from those, we can also get something called parametric equations. So let's start with a line. Rather than look at a normal vector to a line in the plane like we did in the previous section, we're going to say that we have some line L in the plane, and let's suppose that we know a vector V that's parallel to that line. So this image here kind of illustrates that. In addition to that, let's suppose that we know one point on that line. I'm going to let x naught represent the position vector that has that known point as its terminal point. So really x naught would be a vector that looks like this. Okay. And I'm going to let x, even though you're not seeing it here, be the position vector for any arbitrary point on this line L. So I could choose x to be here, for example, and then this would be the position vector. Okay? So the vector x minus x naught would be parallel to that line, which we can see because the initial point would be here at x naught and the terminal point would be here at x. The vector would be completely on that line, which would imply that it's parallel to the vector v, because v is also on that line or parallel to that line. So that means that we could write x minus x naught equals tv for some scalar t. Now, if we let x vary, because remember x is an arbitrary point chosen on that line, then this will correspond to tv for different values of t. So if we let t vary amongst the real numbers, that'll give us all the possible values of x that lie in this line and trace out that entire line. Solving this for x, we can write this as x equals x naught plus tv, where t is any real number. This would be the vector equation for a line. And remember, this is the arbitrary point. This is the position vector for an arbitrary point. Here's the position vector for some point that's known on the line. And v is any vector that's parallel to that line. Okay? As we did in the previous section, we single out the case where the line passes through the origin. So in the event that the line passes through the origin, we could use the origin as our known point, which would have a position vector of the 0 vector, and our equation simplifies down to x equals tv, like this. Okay? Now, we want to go through basically a similar derivation to come up with the vector equation for a plane. So in this case, let's let W be a plane that contains two non-collinear vectors, v1 and v2. The reason they have to be non-collinear is that if they are collinear, that meaning the two vectors are parallel to each other, then there's an infinite number of planes containing those two collinear vectors. You can think of the line that would pass through both vectors as an axis of sorts, and then you could put a plane in 3 space that contains that line and rotate it around that line as if it were an axis, and or like an axle. You can even think of it that way. And all the planes that you get from doing that rotation would contain those two vectors. So if you want a unique plane, you need two vectors in the plane that are not collinear. In that case, if we have those two non-collinear points or vectors in the plane, and if we also have a single known point in the plane, and if we let x naught be the position vector for that known point, then we can come up with a similar vector equation like we did previously. Okay. Now, like we did before, x minus x naught. Let's look at that. So this image might be a little bit difficult to see because the vectors are very close to the same color as the plane, so they kind of fade a little bit. But here's x naught, here's x. even though x naught and x as position vectors aren't necessarily in that plane, the difference between x and x naught would be, because x minus x naught would have its initial point and terminal point both contained in that plane, so the entire vector would be in that plane. We showed previously that if you have two vectors in a plane, then any linear combination of those two vectors would also lie in that plane. So what we're seeing here in this image is that the vector x naught minus x, this guy right here, can be written as a linear combination of the vectors v1 and v2. So that means we scale v1 and v2 appropriately and then add them so that the parallelogram it creates has a diagonal of x naught minus x, or sorry, x minus x naught. That allows us to write our vector x minus x naught as a linear combination of v1 and v2. Adding v naught to both sides, we get this as our vector equation for a plane. So again, if you have two known non-collinear vectors parallel to the plane, v1 and v2, and a known point with position vector x naught that's in the plane, then this will give us the equation for the entire plane, and t1 and t2 are parameters that are allowed to be any real number. Okay, once again, we're going to single out the case where we're talking about a plane passing through the origin. In that case, you can let x not equal the 0 vector, and we get this simpler looking equation. X equals t1v1 plus t2v2. Okay, now the equations that we've been writing, we've been calling those vector equations. But if you were to substitute in for the x naught and the v1 and the v2, or the v in the equation of a line, if we substitute in their component forms and then simplify, we get what's called a parametric equation. So I'm going to do a couple of examples where we find parametric equations. Let's suppose that we want to find the parametric equation of the line parallel to the vector 1, 0, negative 4, and containing this point. So this point is going to give us the components of the position vector for that point. So remember, the equation for a line is going to be x equals x naught, like this, plus tv, where x naught is -2, 5, -1, and v is 1, 0, -4. So I'm going to substitute some things in here. X, remember, is an arbitrary point on this line, and notice the points that we're talking about are ordered. We have ordered triples. So this is talking about a line that's in 3 space, not a line in 2 space. Even though our derivation on the previous page had an image of a line in 2 space, we actually don't need that line to be in 2 space for this equation to hold. It still works in 3 space. There's nothing about that derivation that actually required us to be thinking of our line in 2 space. So I can still apply this. The vector x in component form, because it represents the position vector for an arbitrary point on our line, I can write that as x, y, z. Okay? X naught is -2, 5, -1, plus t times v, which would be 1, 0, -4. This can be written as x, y, z equals -2 plus t. This would be just 5 plus 0t, so I'm not going to write that. And then -1 minus 4t. Okay, and I can let my equation stay in this form. Oftentimes when we have parametric equations like this one, we separate it out into 3 equations, and I can write x equals -2 plus t, y equals 5, z equals -1 minus 4t, and treat that as 3 simultaneous equations. That's another way of representing this exact same equation. Okay, let's try another example. This time we want to find the parametric equation of a plane that passes through the origin and is parallel to the vectors 1, 1, 1 and -2, 0, 3. So in this case, we see that we're passing through the origin. That means I get to use that simpler equation for a plane, that simpler vector equation. That's this one. X equals t1 v1 plus t2 v2. And in this case, v1 is equal to 1, 1, 1. And v2 is equal to negative 2, 0, 3. So putting this into our equation and rewriting x as x, y, z, my parametric equation looks like t1 times 1, 1, 1 plus t2 times negative 2, 0, 3. Or simplifying things down, x, y, z. I'm going to combine all this into a single vector on the right-hand side. This is going to look like t1 minus 2 t2, t1 plus 0 t2, so I don't need to write that, and then t1 plus 3 t2. Okay, now I want to establish a connection between a couple of things here. First of all, if you look at the right-hand side of this equation or the right-hand side of this one, it looks pretty much the same as the parametrized solution to a system of linear equations that has an infinite number of solutions. So that's where we're going to start drawing the connection between these lines and these planes with solutions to linear systems. In addition to that, this right-hand side can be represented either this way or this way. In this notation, I'm writing everything as a single vector, and then I could substitute in values for my t1s and my t2s in order to get individual points on that plane. Up here, I'm writing in a different notation that's actually more useful to us in linear algebra. I'm showing that the plane, this plane in particular, is the set of all linear combinations of the vectors 1, 1, 1 and negative 2, 0, 3. Where here t1 and t2, they can be any real number, right? So that would consist of all possible linear combinations of those two vectors. In chapter 4, we're going to define this plane as the span of these two vectors. You'll hear that word span a lot in chapter 4 and onward, and a span is just a set of all possible linear combinations of some set of vectors. Okay, really, really important concept for this class. All right. We only have a little bit left to cover in this section, so let's now start looking at homogeneous linear systems. So let's suppose that A is an m by n matrix, and we're going to name its rows R1 through Rm, and then I'm going to let x be some vector in Rn. And I want to think about the homogeneous linear system Ax equals 0, okay? Well, if I were to write A as a partitioned matrix, it would look like a column vector, even though it's not a column vector, but with R1, R2, R3, and so on. And I'm multiplying that to the vector X. We know from our definition of matrix multiplication that the result is going to be a column vector in Rm, not n, where each row is the dot product of a row of A with R vector X. So R1 dot X, R2 dot X, and so on. However, because this is a homogeneous linear system, each of these dot products should be coming out to 0. That's because we have the 0 vector on this side. So what does that mean? Well, in light of section 3.3, that tells us that X is a solution to that linear system if and only if X is orthogonal to every row of that matrix A, that coefficient matrix A. Remember, that's what it means for the dot product of two vectors in Rn to be 0. So when we're talking about a set of solutions to a linear system, specifically a homogeneous linear system, we are specifically talking about the set of all vectors that are orthogonal to every row in A. It's an interesting way of geometrically characterizing those sets of those solution sets. Okay, so let's keep that in mind. Now let's look over here. What I'd like to do is take this matrix A, so I have a 3 by 3 matrix A, and form two systems of equations using the same matrix. The first is going to be a homogeneous linear system, and the second is going to be just a general linear system, but with the same set of coefficients, just a different set of constants that it's equal to. Okay? So in order to solve this, I'm going to set up an augmented matrix. So I have 1, -2, 4, -1, 2, -4, 3, -6, 12. And then because we're doing the homogeneous system first, that's going to have all zeros here. All right. Now I'm going to do something that you'll see me do again in the future. I'm going to do all of my Gauss-Jordan in one step. And I'm simply going to write this here, G, J, which stands for Gauss-Jordan, and it's just showing what I'm using the Gauss-Jordan process to get from here to here. But Gauss-Jordan is actually only 2 steps in this case anyways. My top row is going to remain the same. We know that when we do Gauss-Jordan on a homogeneous linear system, the zeros here are going to remain zeros the whole time, so there's nothing really to do there. Both rows 2 and row 3 are proportional to this row up here. That means that I can add a multiple of this row to this one and a multiple of this row to this one and get a row of zeros down here. I'm going to end up with zeros. Okay? Now I have one leading variable and 2 free variables. So if I think of this as x1, x2, and x3, I'm going to set x2 equal to the parameter s, x3 equal to the parameter t, substitute those into this equation up here, and solve for x1. And you know what, this should be a negative here. I almost missed that. So -2, -2. So this is going to say x1 minus 2s plus 4t equals 0. But solving for x1, I get 2s minus 4t. So that means I can write my solution set in vector notation parametrized by these two parameters here. My solution set looks like 2s minus 4t st. Okay, but if I want to write that slightly differently, if I want to write this as a linear combination of vectors, then I can write this as s times the vector 2, 1, 0 plus t times the vector -4, 0, 1. Make sure you're okay with how I did that. All right, this is a process that we do a lot in this class where we have a general solution set, but what you want to do is split it up into a sum of 2 vectors, one containing only the s terms, one containing only the t terms, and then pull the s and the t out the way that I did here. Okay? So let's think about this for a second. What we're saying is that the solution set to this homogeneous linear system is exactly the set of all linear combinations of the vectors 2, 1, 0 and -4, 0, 1. But notice this is a vector equation. This is a if I think of this as v1 and v2, and these are 2 parameters, then this is the equation of a plane passing through the origin. Okay, so what this is showing us is that the solution set to this linear system, this homogeneous linear system, is simply a plane passing through the origin. Now let's look at the other system of equations. 1, -2, 4, -1, 2, -4, 3, -6, 12. And this time it's not homogeneous. I'm going to use this column vector 1, -1, 3 for my constants, and I'm going to use Gauss-Jordan again. If I perform the same 2 operations, the same 2 row operations that I did up here, I'll get rows of zeros down here, and my system ends up looking like this. I'll have zeros here and here. Make sure you're okay with the matrix that I'm getting here. It's an easy Gauss-Jordan, but I'm just sort of jumping to the row echelon form here. So now let's come up with our solution set. Again, I have the same leading variable, same two free variables, and the only difference is that instead of having a 0 up here, I have a 1 up here. This is what changes in my solution set. Instead of 2s minus 4t, I have 1 plus 2s minus 4t. x2 will equal s, x3 will equal t, and my solution set in vector form is going to look like 1 plus 2s minus 4t, st. But if we write that as a linear combination, that's going to look like 1, 0, 0 plus s times 2, 1, 0 plus t times negative 4, 0, 1. Okay? Compare these two. What comparison can we make? Well, notice the only difference between the solution set of my homogeneous linear system and the solution set of this more general linear system, both of which have the same coefficient matrix, is this 1, 0, 0. That's the only difference. Both of them involve a linear combination of the exact same two vectors. But in this case, I'm also adding this additional vector, and this vector turns out to be a specific solution to the original system of equations. You can verify that by writing this as a system of equations and plugging in 1, 0, 0 to see that it works. Okay? It should be fairly straightforward to check that. So if this is a plane passing through the origin, then this is that same plane, but every position vector giving me a point in that plane is being added to this vector. This vector acts as what we call a translation vector. It takes the entire plane and it doesn't change its direction, but it translates it through space. It moves it. That looks like this down here, this image. So we're going to walk through a theorem that kind of proves this result that we're looking at. But if you can see this here, there's a plane down here, and that's a 0. That represents the origin. That plane represents the solution to the homogeneous linear system ax equals 0. But for a general linear system, ax equals b, the solution set will also be a plane, and it's going to be a plane that's parallel to this one, the solution set for our homogeneous linear system, and it's translated by a vector x0, where x0 is just some solution, some specific solution to this system. Okay, it gives us a very interesting characterization of solutions to linear systems, geometrically speaking. So let's talk about this theorem straight out of, actually, I think an older version of the book. I think the new version left this theorem out, but it's so interesting that I wanted to include this. This is saying the same thing we just said. The general solution of a consistent linear system ax equals b can be obtained by adding any specific solution of ax equals b to the general solution of ax equals 0. If you've had differential equations, this process should feel very, very familiar, and that's not a coincidence. Okay, but I'm just going to leave that at that. Let's prove this. Let's suppose that x0 is any specific solution to the general linear system ax equals b. And we're going to let w denote the solution set of the homogeneous linear system ax equals 0, the homogeneous system that has the exact same coefficient matrix as this one. Now we're going to introduce some notation here that's common in abstract algebra courses. We haven't used it here, but we're going to define it. So I'm going to let x0 plus w denote the set of all vectors that result from adding x0 to a vector in w. This is a weird notation because remember, x0 is a vector, but w is a set. It's not an individual vector by itself. It's a set of vectors forming this solution set. So this thing is defined to be a set. It's the set of all vectors that can be written as a sum of x0 plus a vector in that set w. Okay. Now what we need to do is show that if x is any vector in x0 plus w, then x is a solution to our system ax equals b, because that would actually just establish this entire theorem. or one direction of it anyways. Conversely, we also need to show that every solution of ax equals b is in this set. So in other words, this set should define the solution set to ax equals b. So going the first direction, let's assume that x is just any vector in here, x naught plus w. That means that there's some vector in w, let's call it w, or let's just call it lowercase w, such that x can be written as x naught plus w. That's how we defined that set right there. Okay, now we made the assumption that x naught is a solution to the system ax equals b. So that means that ax naught will equal b. In addition, remember w is the solution set to our homogeneous linear system. So aw should equal 0. What that tells us is that ax, which would be equal to a times x naught plus w, because this is a way of expressing x as a sum. We can distribute the matrix A in there. This will come out to b, this will come out to 0, and so their sum is equal to b. That shows that the vector x, which we chose arbitrarily from this set, is a solution to the the general linear system ax equals b. Going the other direction, let x be any solution to that general linear system. Now we need to show that x belongs to this set. So if you remember in our preliminary section, the reason we're doing this in both directions is because we want to prove that two sets are equal to each other. We want to prove that the set of solutions to this linear system is equal to this set that we're calling x naught plus w, which is another way of stating the original theorem up here. So far, we've proven that the set x naught plus w is a subset of the solutions to this equation, but now we want to prove that the solutions to this equation is a subset of x naught plus w, giving us set equality. So to that end, we've assumed that x belongs to the solution set of ax equals b, and now to show that x belongs to the set x naught plus w, we have to find a vector w that belongs to capital W such that our solution x can be written as a sum of x naught plus that lowercase w. That's the property that would put it here. Okay? Well, what we can do is we can define w using this equation to just equal x minus x naught. Remember, x is a vector that we chose from this solution set. X naught is a vector that we know is a solution to the homogeneous linear system. And if this is to hold, then w should equal x minus x naught. Now we just plug it in to see if it works. So if we plug in w, let's see, so this confirms what we just said. The vector w satisfies 22. This is called, we're using a 22 to denote this equation right here. And we know that w belongs to the set capital W because the set capital W is a set of solutions to our homogeneous linear system. Plugging that in and following these steps, A will distribute again. We get B minus B, which equals 0. That wraps up this whole proof. Okay. Hopefully that made sense. So again, this is really, really important when we're trying to visualize solutions to linear systems. A solution to a linear system if we have, sorry, let me go back to the specific case. Our solution set here was a linear combination of two non-collinear vectors. These two vectors are not parallel, so the solution set would look like a plane. If instead of having this system of equation or this plane pass through the origin, if we had it pass through some other point, then we'd be looking at the exact same plane but translated by a vector. So we would get a case like this where the two planes are parallel to each other. Okay, that's going to wrap up section 3.4.